loss per unit frequency, this divided by this. So and the x-axis and y-axis scale I'm giving here, so that you should not everybody should get same kind of plot. So I want that all of you use the graph paper, all of you um, means on along the y-axis, sorry, along the y-axis you should have iron loss per unit frequency, and along the x-axis frequency. So first of all, you should get a table between frequency and iron loss per unit frequency. So you'll get the data points, and these data points you are required to plot. I want that all of you should plot it. And scale, this scale, in plotting this scale you should use. This is given to all of you. By the time I will take your attendance. I don't know how many of you joined till now. Many of you are there. So you draw this diagram. By the time I'll take your attendance. Roll number 1.
Present, sir.
2.
Present, sir. Roll number 2, present, sir.
3. 4.
Present, sir. Roll number 4.
5.
Present, sir.
6. 7. 8. 9. 10. 11.
Present, sir.
12. 13. 14.
Yes, sir. 14.
15. 16.
Present, sir.
17. 18.
Yes, sir. 18.
19.
Present, sir. 19.
20.
Yes, sir. 20.
21.
Yes, sir. 21.
22. 23. 24. 25.
Present, sir.
26. 27.
Present, sir.
27 is present.
Yes, sir.
Okay. 28. 29.
Present, sir. 29.
30. Anybody else on from row number 1 to 30?
Sir, 26.
26. Okay. Anybody else? Now roll number 30. Between iron loss per kg per unit frequency and frequency itself. आपने ड्रॉ किया भाई? ये ड्रॉ करना था आपको, जो आयरन लॉस दिया हुआ पर केजी उसको फ्रीक्वेंसी से डिवाइड करना है, एंड देन you have to plot it on a simple graph paper against the frequency. जी, किसी ने किया? This is the scale I had given you. किसी ने भी नहीं किया? Anyway, it is up to you. If you want to learn, then as you know that equation is a straight line equation that I had written earlier. I had shown you that this will be straight line equation only when your flux density is constant. So you'll have this kind of equation, M plus NF so by plotting the, because you know we'll get in a straight line like this when you'll draw that these points, and somewhere this straight line will cut the y-axis, so that will be M, intercept on the y-axis by the straight line. So this will be the M. So from here we can find out M as per the given scale, and then any 2 points we can take the on the straight line, and then we can find the slope of it, y2 minus y1 upon x2 minus x1. So that will be n. And once from this plot you are able to find out these two values, the intercept on the y-axis and the slope of the straight line, then you know this part represents the hysteresis loss per unit frequency, and this whole part represents the eddy current loss per unit frequency. So by multiplying it with the corresponding value of the frequency, this M, we can find out the hysteresis loss, and by multiplying n by the frequency square, we can find out the. So this is how the eddy current loss and hysteresis loss are separated from the iron loss using graphical method. तो अगर किसी ने प्लॉट किया है, then tell me what is the intercept with the y-axis. हैं? जी कितना आया? I had given you the x and y axis scales. जी कोई बताएगा भाई? Anyway, so this is how you will divide, and then you'll draw on the graph paper like this kind of trace you'll have on the graph paper. So from that graph paper you'll find M and N. So here you can see that from the graph we are getting here K1 and K2 I have taken. The K1 is 0.068 from the graph paper, and this is the slope, 2 points we have selected, and So point, this is with respect to zero frequency, that is on the y-axis, and this is with corresponding to the 50 hertz point. So the slope is coming out to be, that is your K2 here, 0.00104. Now hysteresis loss at 50 hertz, it is and 1 Weber per square meter. It is we just multiplied it by the 50 hertz and we got it. Similarly, eddy current loss at 50 hertz, square of the frequency. Now in the second part, we are changing this a maximum flux density. Instead of flux density of 1 Weber per square meter, now we want for the same sample, now we want these two losses at 1.2 Weber per square meter and at 60 hertz. So here in this case, you will see, as far as hysteresis loss is concerned, it is the maximum flux density times Steinmetz constant, that is given in the problem 1.6, and frequency, product of these two. So whatever hysteresis loss for the same sample we have calculated for 50 hertz and 1 Weber square, what we did, we divided it by the 50 hertz and multiplied by 60 hertz, and Weber per square meter is now 1.2. So this is the simple arithmetic as far as this part is concerned, and then we got the hysteresis loss. Similarly, eddy current loss is directly proportional. Now here why I'm putting form factor here. Here you see form factor also changed. 60 hertz form factor of the flux wave is 1.2. So earlier it was pure sinusoidal. Here you can see it was purely sinusoidal. It was written here. Now purely sinusoidal means 1.11. Now when you're not having purely sinusoidal but the distorted waveform, then its form factor one is changed from 1.11 to 1.2. This won't affect the hysteresis loss, but your eddy current loss depends upon the waveform, shape of the waveform also, because it will have the harmonics. Obviously it is not if it is not purely sinusoidal, then it will have higher order harmonics. So because of the higher frequency harmonics, eddy current losses will increase. So here you see in this case your eddy current loss is directly proportional to square of the form factor into your frequency, square of the frequency, square of the flux density. So accordingly, using arithmetic formula, because in this case it was 2.6 watt per kilogram. Now we multiplied it by the 1.2 and divided by 160 hertz, 50 hertz, and form factor 1.2 upon 1.11. So in this way we found 6.3 watt per kilogram. So the as far as this B part is concerned, although for solution it is necessary, but as far as the graphical method is concerned, that is only the A part. And if you are able to solve this problem, means the main emphasis in this case I'm putting on the A part, because it is with the help of graphical method we are trying to separate the eddy and eddy current loss and hysteresis loss. So that if that is clear to all of you, then fine. If anybody is having any question regarding this problem, especially the graphical method to separate the hysteresis and eddy current loss, you can ask please. जी बताइए. हाँ भाई, क्योंकि आप लोगों ने प्लॉट किया नहीं, so I don't know how much you are able to understand, but still if you are having any query, you are welcome. हाँ भाई, कुछ पूछना है? नहीं पूछना है. Anyway, now I started the AC bridge method to measure. So there are two objectives. One is to measure the to separate. Once you are able to measure the iron loss, then you are required to separate it. So for that we had discussed the method. Now, as far as the measurement of iron loss is concerned, so the conventional method, as I told you, that it is a open circuit method, where whatever sample we get, we make a core out of it, and then we wind the primary and secondary windings, and then we perform the open circuit test on it, and whatever voltage that is consumed by the sample, when energized, um, through one of the winding, and other winding is kept open, then it is basically the iron loss. Means there is small error in it. Means you have to subtract the no load copper loss from the wattmeter reading, and then you will get the iron loss in the core. But this open circuit test is not always possible when the sample is small, and laminates are not made, like ferrite cores we use at the higher frequency instead of silicon steel, crgo silicon steel, that is good for the 50 hertz, at 50 hertz frequency, but we cannot use at the higher frequency like audio frequency and all. So we use ferrite cores, and ferrite material is basically in form of the powder form, and they are basically casting is done to make different shape of the core. So for such type of samples, bridge method is used, and I had shown you on the last turn, I discussed it. Here you can see that it is Maxwell's inductance comparison bridge we have used, and with the help of this, um, uh, we are able to find out the resistance and inductance of the sample. This is your sample. This is your sample. So resistance and inductance we are able to find out, and then we are able to find out the iron loss. Here this is the formula. Basically this is the formula for the iron loss, because the branch current is one of the bridge branch current is there, that we transformed into basically the total current, because it is easy to measure the total current. Branch current is difficult to measure, so that reading we can very easily we can have. So it is from the balance equation, from the this KCL equation, and then from the balance equation we are having, I1 is basically written in terms of the total current, and then accordingly this is put here in the formula, and then we got the iron loss. So if anybody is having any queries regarding whatever we discussed on the last week, up to this I discussed on the last turn, so you can ask anybody anything. किसी को कुछ पूछना है तो पूछ लो भाई. Otherwise, there is one small extension to it that we'll discuss here. We can use this bridge method even to find out the permittivity, rather permeability of the material. Here you can see that as far as the sample is concerned, so it is having sample is having n number of turns, and current I1 is flowing through it when the bridge is balanced. Obviously I1 is flowing through it, so the mmf will be obviously n into I1, so that will be equal to phi into reluctance of the circuit. Then we can write phi is equal to ni. This is the now As far as the reluctance is concerned, this is the formula. The mean path, that is basically the circumference of the core, and your relative permeability, and your absolute permeability of the free space, and the cross sectional area of the core. And this thing we had found out the sample of the inductance of the sample value we had already calculated from one of the balance equations. So ls is known, so we can, the self inductance is equal to flux linkage per unit current. So we'll put this phi here in place of, so here you can see that in place of the phi we put it this, and then many, if I1 and I1 is getting cancelled, and then we are able, we are end up with this. So your relative permeability can be by, from this equation, by rearranging the terms, relative permeability can be written as the sample inductance divided by the permeability of the free space, mean length of the magnetic circuit, that is core circumference, and square of the number of turns and cross sectional area. So you can find out the permeability of the sample also, along with the, although our main objective was to find out the iron loss. So the one of the method to find out the iron loss and is AC bridge method, and along with that we can measure the permeability also, sample permeability. And although the main method, I'm again reminding you, it is the open circuit method, that is also called wattmeter method. So through wattmeter we measure the loss. So this is how AC bridge can be used for measurement of um, loss and iron loss, and the permeability also can be used. And this found iron loss can be separated using either by solving the equation, you need data points obviously in all both the cases, or by the graphical method. So if you are having any query regarding these topics, you can ask please. There are some more topics in the magnetic measurements, but right now after covering these topics, I'm switching to the another important topic of this unit, that is oscilloscope. Then we'll later on we'll discuss other topics also. So oscilloscope, all of you are aware with the oscilloscope. Okay, are you agree with me? All of you must have worked on oscilloscope also, and means you must have operated the oscilloscope in different laboratories. And what is your impression about the oscilloscope, what it is? If I'm asking, somebody is asking a question, what is oscilloscope, what will be your response? Anybody? जी नहीं, कुछ बोला तो करिए आप लोग, हैं? बताइए, what is oscilloscope?
सर सम वेव फॉर्म हम एनालाइज कर सकते हैं,
वेव फॉर्म्स
एनालाइज कर सकते हैं सर,
एनालाइज कर सकते हैं। ओके, गुड, वेरी गुड। कौन सी वेव फॉर्म, किस चीज की वेव फॉर्म?
सर इलेक्ट्रॉनिक सिग्नल।
इलेक्ट्रॉनिक सिग्नल, क्या होता है इलेक्ट्रॉनिक सिग्नल? ये जो वेव फॉर्म है, सिग्नल है, ये होता क्या है जिसको आप कह रहे हैं डिस्प्ले कर, एनालाइज कर सकते हैं?
सर चेंज, कोई भी वोल्टेज चेंज जो भी सिग्नल्स होती है उसी को हम इसमें देख एनालाइज कर सकते हैं।
अच्छा, चेंज होते हुए सिग्नल को वोल्टेज सिग्नल आप कह रहे हैं. एंड व्हाट अबाउट करंट सिग्नल?
The same with I think current signal also.
So you can analyze the current signal as well as voltage signal.
Yes, sir.
Okay. Anybody else want to add something? So you see, oscilloscope is basically the eye of electrical and electronic circuits, you can say. This is the eye. Many things which you cannot see, although it is happening in a circuit, electrical and electronic circuit, but you cannot see on your by your naked eyes. Like somebody is saying that the voltage is present in a circuit, you are energizing the circuit by a voltage source, and then you are saying that the sinusoidal voltage and sinusoidal sinusoidal voltage is applied, and that is causing the sinusoidal current to flow in the circuit, but you cannot see it by the naked eyes. So these voltage and current we are talking about, they are basically signal. They are commonly they are called signal. And as far as the oscilloscope is concerned, oscilloscope basically displays the voltage signal, not the current signal. Oscilloscope displays, it traces the voltage signal on its screen, and if this signal is time varying, then a time varying signal can be, means if a wire is carrying a sinusoidal voltage, it is having a sinusoidal voltage signal, then you can see this voltage signal on the screen, that how this voltage signal is varying with time. Now I'm coming to the current signal. If you want to see the current signal, then you have to convert it into the voltage signal. Only then you can apply to the oscilloscope, so that it can be seen. And then only the display is not the objective. It is displayed, it is one of the objective to display the time varying voltage signal. Even DC signal we can also display um, on the oscilloscope. It is not like that DC signal you cannot display. You can display DC signal also, but mostly DC signal display is having no meaning. Only thing is that you'll see that how much voltage is there. But as far as the time varying signals are concerned, one more important thing I would like to tell you, that for a stable live running display, means you can display two ways. Means as far as digital oscilloscopes are concerned, in analog oscilloscope only one way, there is live or running mode displays there. But in digital oscilloscopes, it is possible to have a frame of it. Means you can capture a frame, a screen of the oscilloscope. So that is called stationary mode, means it is not running mode. um, as far as the stable display is concerned, oscilloscope, this is a very important thing that you should keep in your mind. Oscilloscope can display only the periodic time varying signals. Periodic time varying signals. You understanding what I'm saying? The oscilloscope can display faithfully, and stable display is possible only for the um, uh, time varying signal when it is periodic in nature. There are many time varying signal which are not periodic. We call them random signal. We call them random signal. It means they are not following any pattern. They are not following any pattern. Like sinusoidal is a periodic signal. Your square wave is a periodic signal. Your triangular waveform is a periodic signal. So oscilloscope can display periodic signal only, means faithfully, in running mode. And if your signal is not periodic, then stable display is not possible. Time varying signal I am talking about. Now, if you think it's a very important topic for all of you, and it is very interesting also. And after means you must have faced difficulty in operating oscilloscope. Although oscilloscope is a standard equipment, means this is used for measurement of many parameters. It is a one instrument army, you can say. It is a one instrument army. It can be used to measure many things, many things. You will see. We'll discuss some of the application. So you can measure the voltage, you can measure the current, you can measure frequency, you can measure um, means uh, phase angle, you can measure hysteresis loss. Many applications are there. Many applications. You can use it as a detector in the bridge circuit. Whether bridge circuit, your bridge is AC or DC, its resolution is very high. So it is a very accurate kind of instrument, and it is a very versatile instrument, you can say. Versatile instrument. And I'll try to make you understand what is its construction, how it works. Then you'll be more comfortable in using oscilloscope, because it requires certain kind of expertise. So it is generally not preferred by the in general by people avoid the use of oscilloscope. So you can use oscilloscope in place of ammeter, in place of voltmeter, and many things is possible. So I discussed many things, and point wise it is written here. Oscilloscopes convert electrical input voltage signal into the visible trace on a screen. So it basically displays only the voltage signal. If you want to see the current signal, then you should means convert it into the voltage signal. Can anybody tell me what is the easiest way of converting current signal into the voltage signal? कोई बता सकता है भाई? जी, कोई करंट सिग्नल है, उसको वोल्टेज सिग्नल में कन्वर्ट करना है, कैसे कन्वर्ट करोगे? आप लोग तो यार बोलते ही नहीं हो, न बोलते हो न सुनते हो, हैं? आपको मालूम है ना, सुनने वाला ही बोलता है. जी, very few people are present and they are also not speaking. अगर कोई किसी वायर में current 5 ampere current, sinusoidal current is flowing, how will you convert it into the voltage? अच्छा, तो पॉसिबल नहीं है. हम करते क्या है भाई कि उसको किसी रेजिस्टेंस में ड्रॉप करा दिए. दिस इज द इजीएस्ट वे. अगर 5 एम्पियर करंट फ्लो कर रही है, तो हमने एक रेजिस्टेंस 1 ओम का लगा दिया सपोज. तो 5 एम्पियर करंट जो है 5 एम्पियर है, और उसको हमने पास कराया 1 ओम रेजिस्टेंस से, तो 5 वोल्ट ड्रॉप हुआ है ना. 5 वोल्ट यहाँ ड्रॉप होगा, और इस 5 वोल्ट का भी नेचर वही होगा जो 5 एम्पियर करंट का, एज फार एज द वेरिएशन विद रिस्पेक्ट टू टाइम इज कंसर्न. तो हम क्या करते हैं, इसको इसके अक्रॉस फिर इसको हम ऑसिलोस्कोप में दे देते हैं. ये अगर हमारा ऑसिलोस्कोप है, तो ऑसिलोस्कोप के किसी चैनल पे अप्लाई कर देते हैं. इसी चैनल पे हम उसको अप्लाई कर देते हैं। तो the way your current is varying, because there is no phase shift, no modification across the resistors we are taking. So 5 volt जो है वो आपको ड्रॉप होगा इसके अक्रॉस, एंड दैट वी कैन, सो दिस इज हाउ द करंट इज कन्वर्टेड इनटू द वोल्टेज. जनरली दिस इज डन in the case of, in case if you want to see the although there are the methods which are used for measurement for convert, there are the circuits, dedicated operational amplifier based circuit. You can convert the current signal into the voltage signal. So that but the simplest way, this is the simplest way, and this is not, although this is not a very good way, because whenever you will pass a current into the resistance, losses will take place, so you lose energy, and if you don't want, then the operational amplifier based circuits are there. Anyway, so if anybody is having any question, you can ask. This is one of the way, easiest way, and that is generally done. So this is how means if you want to see a current signal, then time varying current signal, then you have to convert it into the voltage signal, and that is the easiest way. Then oscilloscope plots time varying periodic voltage. This is emphasis on periodic. It's very important that you should, if it is not periodic, you cannot, although it will be plotted on the screen, but it will not be stable, it will be unstable. It is not possible to plot a stable time varying display a non-periodic time varying voltage signal on the oscilloscope screen, because technology is like that. So oscilloscope plots the time varying periodic voltage signal in 2 dimension. Typically 2 dimension means voltage versus time, generally voltage versus time. Oscilloscopes, I'll come to that. It is not only it only, this is one of the use, one of the way, one of the operating mode in which the voltage is the time varying voltage signal is basically plotted against the time voltage, against the time. But there is another way this oscilloscope is used. I will come to that. Oscilloscopes are used by engineers and technicians to test, verify, and debug electronic circuits. So this is all possible. Now this I tried to find out very simple oscilloscope block diagram. Although oscilloscope is having much more hardware than whatever I'm showing here, but these are the essential parts. Whatever things I'm showing here, components I'm showing here of the oscilloscope, they are essential part. They are required in an oscilloscope. So if you are able to understand means working of the oscilloscope, we can understand with these many components. These are the, so heart of the oscilloscope is basically CRT, cathode ray tube. This is your cathode ray tube, and it is having an electron gun which emits basically electron you can say beam. And this electron beam, when it strikes on a phosphorescent screen, then energy, because it will have a kinetic energy, it is absorbed by the material, coated material by which your screen is coated, and then it glows. So that glow will see from outside as a trace or as a point. Now apart from that, we are having a electrostatic system to uh, to deflect this electron beam, so that we can have a meaningful trace on the screen. So here, there we are having one set of um, uh, plates, electrostatic plates, capacitive plate, you can say, they, which basically causes the deflection in the electron beam vertically. That's why this pair of plates are known as vertical deflection plates. Then we are having another set of pair of plates. It is basically, it causes the deflection when the voltage is applied across it. Then it causes the deflection in the electron beam horizontally. So with this two pairs of electrostatic systems, means plates, we can deflect the with the suitable application of suitable voltage across these plates. We can deflect the your electron beam horizontally as well as vertically, and this deflection will cause a trace on the screen. By interpreting that trace, we can find out the many information. So if anybody is having, I just discussed only the parts inside the CRT. If anybody is having any question, anything regarding this part, you can ask, please. Then we are having other parts also which are outside uh, the CRT. जी बताइए. हाँ या नहीं, कुछ नहीं. Anyway, now other parts are the signal. Actually, signal which we want to display on the screen is basically applied to the vertical plates. This is another information that I'm giving you. Keep in your mind. We'll refer to it many times. So then basically whatever signal we want to display on the screen, time varying voltage signal, it will apply to the vertical through vertical amplifier and the delay line. So this vertical amplifier is basically, it scales the voltage because we require very small voltage variation across the vertical plates to deflect the screen, to deflect the electron beam which covers the whole screen. So we scale, if basically your signal is very small, then it will be amplified to the sufficient level, and if it is very large, then it will be attenuated to the sufficient level which is required to deflect the obviously the vertical deflection represents the amplitude of the signal which you are so we have to, because here a very small voltage is required to deflect the electron beam across the full screen. So we, in any case, whatever your signal is high or signal is low, we have to scale it down or up to the required level so that the meaningful and proportional deflection on the screen can be seen. This is one part. Then another part is your vertical deflection. So vertical deflection, whatever here these diagrams are basically applicable to um, uh, for one of the, because your oscilloscope can be used in two modes. One mode is XY mode. Here I have written, I think somewhere, oscilloscope is operated in two mode. YT mode. YT mode means, this is the most common mode, means YT mode means when you are plotting the time varying voltage signal against the time. That's so Y is amplitude and T is, so along the x-axis it is a time screen and y-axis it is a amplitude screen, sorry, axis. And then we are having it is another way, we can have XY mode. So we can have two time varying signals. One is applied across the, so as far as YT mode is concerned, in the YT mode, this whole diagram is for the YT mode. So your signal is applied across the Y plates, and how can we have the time scale on the along the x-axis in YT mode? This is all for that. So here and in XY mode, we can plot one time varying voltage against the other one. Here you see, in that case we have two signals. One signal is applied to the Y plates, and then these things will not be present. Then we'll apply another signal through the horizontal amplifier to this. So that is called Y. We'll come to that again many. So here only thing that is important, that um, whatever block diagram I had shown here, it is for the YT mode of operation. So I'll this is a very important thing. I'll discuss it on the next turn We'll continue from here. So it's very interesting. I want that you try to understand, then you'll have the insight into the oscilloscope, and then it will help you if you'll understand how it works, and what are the different parts and what is their meaning. Then it will helpful in operating the oscilloscope correctly. Okay, so I'm closing today's lecture here, and whatever question you're having, you can ask on the next turn. Okay, tomorrow in the first period. Okay, thank you.
Thank you, sir.